Hi all, myself Dr. K. Ashok, Associate Professor of Physics, Marri Reddy Institute of Technology and Management. Today I am going to discuss about the dielectrics. In the previous session, I discussed about the basics of the dielectrics. There is nothing but basic definitions which are needed to learn the dielectrics. Today I am going to discuss about the different types of polarizations. First of all, what is the polarization? The process of producing dipoles or the separation of the charges is nothing but polarization. Polarization of the charges here taking place. Suppose if you consider a classroom, how we are keeping the students, like all girls are one side, all boys are other side. That is nothing but polarization based on the gender. Here the polarization is happening based on the charges. Whenever we apply a DC field to a dielectric material, four types of polarizations takes place. First one is electronic polarization, next one is ionic polarization, orientation polarization, and space charge polarization. In this session, I am going to discuss about these four types of polarizations. Electronic polarization. You consider an atom. So here, imaginary spherical cavity. Here the charges are symmetrically distributed. The centers of the positive charge, that is nucleus, and the centers of the negative charge, both coincide. Positive charge center where it is, exactly negative charge center is also there only. That's why what is the dipole moment? Dipole moment is 0. First of all, what is the dipole moment? Dipole moment is nothing but, first you observe dipole. This is the positive charge, this is the negative charge separated by a certain distance. Dipole moment is nothing but distance between the charges into charge. Here the distance, positive center and negative center is coincide. That's why the distance is 0. When the distance is 0, the dipole moment is obviously 0. When no field is applied, here no field. When no field is applied, the centers of the positive charge coincide with the centers of the negative charge, dipole moment is 0. Whenever we apply an electric field, whenever you apply an electric field, then electron cloud is slightly shifted, means the spherical shape is converted into elliptical. You can observe here, elliptical. Here indirectly spherical. Spherical symmetry will be there. That's why net cancellation, positive and negative centers are coincide. Here, whenever it is converted into elliptical, then what happened here? The centers of negative is this side and this is positive, positive center and certain negative center. Automatically polarization takes place. How will we define electronic polarization? The displacement of electron cloud and nucleus due to the application of the electric field is known as electronic polarization. The electronic polarization here, it purely depends on the distance of displacement. Nothing but how much displacement happens. More displacement, more electronic polarization. Less displacement, obviously, less electronic polarization takes place. But this electronic polarization is independent of temperature. Coming to second one, ionic polarization. So ionic polarization takes place in ionic crystals. What are the examples of ionic crystals? Simply NaCl. Here Na ion, Na plus. So it loses one electron to gain inert gas configuration. Cl minus, it requires 17 like its atomic number, so that 7 valency electrons are there. It requires 1 electron. So sodium donates 1 electron, chlorine accepts another electron. So by donating, sodium becomes sodium ion. By accepting electron, chlorine becomes chlorine ion. Like this, NaCl crystal is there. Inside NaCl, ions are there, positive and negative ions. When no electric field is applied, but they are separated by, let it be, certain distance. When you apply certain electric field, what happen, electron and this positive ion. Indirectly, cation and anions will displace. Positive ion and negative ion get displaced. Then the distance between these two automatically increases. Suppose this is positive ion, this is negative ion, separated by a certain distance, assume it as x, this distance. But whenever you apply an electric field, automatically this distance will increase. Initially, let it be this is x. X1 is the distance displaced by negative ion. X2 is the distance displaced by the positive ion. So what is the net displacement? Net displacement is nothing but x1 plus x2. So the distance between the ions is increasing automatically. The dipole moment. Dipole moment is nothing but distance into charge. This distance is increasing by here x1 plus x2. Automatically the dipole moment will increase. Basically, what is the ionic polarization means? This happens in ionic crystals. Whenever we apply an electric field, the displacement of cations and anions takes place. Such type of polarization is called ionic polarization. Next, orientation polarization. Certain materials like polar dielectrics, mainly little bit I discussed in previous video also, polar dielectrics. In the polar dielectrics, the dipoles are readily available, but they are randomly oriented. They oriented in randomly. That's why what is the net dipole moment? Net dipole moment is 0. When you apply an electric field, then these randomly oriented dipoles tend to align in the direction of the applied field. Here we are showing in the direction of the electric field, but accurately if you apply the field in this direction, the dipoles will tend to align in this direction. But our main focus is systematic alignment. That is only here focus. Orientation polarization is also known as dielectric polarization because in the polar dielectrics, the dipoles are readily available. These dipoles are randomly oriented. By the application of the electric field, these randomly oriented dipoles align systematically in the direction of the applied field. But it is temperature dependent. Again, if you increase the temperature, these systematic aligned dipoles becomes randomly aligned dipoles. Net dipole moment is obviously 0. This is only the polarization which is dependent on temperature. Next one is space charge polarization. The space charge polarization is nothing but whenever you apply the electric field, the charges will be accumulated on the surfaces of the electrodes. Here, what is the meaning of electrode? Dielectric material, you consider what I told you, this is the insulating material. But if you want to apply electric field to insulator, what we will do, we will keep certain coating here. Conducting coating. It may be platinum or gold or silver. These all are good conductors. These all are good conductors. And again, bottom end also same coating we will keep. These coatings which are used, these are nothing but electrodes. Now we will apply the electric field in this manner. So one is positive, another. These are nothing but electrodes. Whenever we apply the electric field, then what happened means on the electrode some charge carrier. Suppose you are giving here negative. So positive charges accumulated on negative plate. And on positive plate, negative charges will be accumulated. Accumulation of the charges due to the application of the electric field is known as space charge polarization. But space charge polarization is completely negligible. Suppose if you consider polarizability alpha, alpha is nothing but total polarizability is nothing but sum of electronic polarizability, ionic polarizability, orientation polarizability, and space charge polarizability. But this space charge polarizability is an external mechanism which is almost negligible. That's why the total polarizability is nothing but sum of the electronic polarizability, ionic polarizability, and orientation polarizability. Next, we will discuss about the local field, internal field, or Lorentz field. Consider a dielectric material. Consider a dielectric material. You keep the dielectric material in between the plates of a parallel plate capacitor. This parallel plate capacitor, let it be, this is positive and this is negative. Imagine inside you consider an atom. That is the reference atom we are using and studying purpose. And this atom is surrounded by spherical cavity. Now this atom A experiences different types of fields. This atom A experiences field E1. Field E1. E1 is the field experienced by this atom A due to the charges on the plates of the parallel plate capacitor. Next, this atom A experiences another field. That field is nothing but due to the charges accumulated on the surface of the dielectric material. E2 is the field experienced by atom A due to the charges on the dielectric material. E3 is the field experienced by this atom A due to the other atoms present in the material. Due to the other atoms present in the material. E4 is the field experienced by this reference atom A due to the charges accumulated on the imaginary spherical cavity. Like this, atom A experiences not only because of the field provided externally, because of the internal changes in the dielectric material also takes place. So E1 is the field experienced by atom due to the charges. Suppose this is the just now only we discussed. This is the dielectric material. Inside this is the atom A and this is connected to positive terminal and this is connected to negative terminal. Here the charges on the plates are positive, negative. This is the field E. So E1 is the field experienced by atom A due to the charge density on the plates. E1 is nothing but E plus P by epsilon naught. This you take it as equation number 1. E2 is the field experienced by this atom A due to the charges on the surface of the dielectric material. E2 is minus P by epsilon naught because here in the previous case positive charges are up, that's why a positive type polarization I2, and this time the charges here are negative, that's why ulta the sign is negative. E3 is the field experienced by atom A due to the other atoms, but if it is a cubical by symmetry, what is the force experienced by it, you know, automatically 0. E3 is the field experienced by atom A due to the charges on the other atoms present in the material. Next, E4 is the field experienced by atom A. This is the atom A, our reference atom. This is the imaginary spherical cavity. E4 is the field experienced by atom A. That value is P by 3 epsilon naught. So, when we consider a atom and here imaginary sphere, this atom experiences a 4 types of forces. Field 1 is because of the charges on the plates of the capacitor. Field E2 because of the charges on the surface of the dielectric material. E3 is the field because of the other atoms in the material. E4 is the field because of the charges on the imaginary spherical cavity. Now the internal field is nothing but sum of these 4 fields. E1 is the charges on the plates of the capacitor. E2 is the charges on the dielectric slab. E3 is the field because of the other atoms present in the material. E4 is the field because of the charges on imaginary spherical cavity. E1 is nothing but value, and E2 already I wrote minus P by epsilon. E3 because of the symmetry 0. E4 is P by epsilon naught. Positive and negative will get cancelled. So internal field is nothing but EI equals to E plus P by 3 epsilon. This is known as Lorentz field. This is known as Lorentz field, or else this is known as local field in solids or internal field in solids. These are the references what I used. Thank you.